Hello, I'm going to work through the Exam 3 Prep Pop Quiz 10. So these are questions that I received when I did a preview. And I think it does a good job of spanning all the material you are going to be asked about on the exam on Friday. All right, let's start with PH4+. So these are the elements that we're most interested in terms of bonding. Keep in mind, based on the valency model, fluorine will form 1 bond, oxygen 2, nitrogen 3, and carbon 4. Then we have the row 3, which do things a little bit differently, but usually follow very similar trends to the row above it. All right, so when we look at nitrogen, when we look at nitrogen, let me go back to where we were. Sorry about that. Pushed the wrong button, and things got away from me. All right, so we go, it forms 3 bonds, right, with hydrogen, and so does phosphorus. And the justification for that was when we look at the electronic configuration, 1s2, 2s2, 2p3, so to complete the shell, to get neon's core, 3 bonds had to form to complete the shell. Now phosphorus has the same story, 1s2, 2s2, but instead of the row 2, it's in row 3, so it also has to form 3 bonds. Now we would, if the molecule was neutral, we would be building it this way, but because it's charged, we really have 1s2, 2p2, 2p6, 3s2, 3p2, because one of the electrons has left. Because it's left, we now need to form 4 bonds to obtain the argon core. We can do that by building phosphorus this way, like we would carbon or silicon. And by doing that with the positive charge, we would build this molecule, which look very familiar, as a tetrahedron, just like all single bonded carbon atoms. Tetrahedral. No lone pairs present because of the positive charge. Answer C would be true if it was neutral, right? If we were making PH3. So which of these molecules do not have a tetrahedral electronic domain geometry? Okay, so some of them are fairly straightforward to identify. Others are a little bit more difficult. So remember, when we see selenium, I'm asking you to climb the column and say, well, selenium's like sulfur, but sulfur is like oxygen. So H2 selenium is just like, H2 selenium is just like H2 copper. Just like H2O. Right, so that's definitely a tetrahedral electronic geometry. It only has single bonds around the central atom, 2 lone pairs. So tetrahedral, bent, right? But bent molecular, but tetrahedron electronically. Right, any carbon-containing molecule with 4 single bonds is going to be a tetrahedron. NH3, we just kind of talked about that. If it's neutral, it's going to form 3 bonds. It's a tetrahedral. NH3 is an electronic tetrahedron, but molecularly it's trigonal pyramid, but it's still a tetrahedron with that lone pair considered a domain. The final one is the tricky one. Now, when we try to build the Lewis structure, we did this in class to try to put the electrons around here. Problem was oxygen had 8 electrons, but sulfur only had 6. So we delocalized to form a double bond here. And then we recognize this as a resonance structure because there's a single bond, double bond, but it is not an electronic tetrahedron. It's an electronically trigonal pyramid, no, like trigonal planar. so no, SO2 is not an electronic tetrahedron. It forms a resonance structure. So just keep in mind resonance. Remember, this has additional stability. Additional stability. The argument was kinetic energy goes down because delocalization. Bigger volume. Potential energy goes down because delocalization leads less electron repulsions, and total energy goes down because potential energy plus kinetic energy went down. So that's the story behind all bonding, but for resonance, because it's it's extended over a larger volume, it has an additional contribution. So that would be our energy argument for resonance. And remember, any molecule that has resonance cannot be a tetrahedron. It has to be a single bond. It has to be a trigonal planar, single bond, double bond molecule. Here we want to know which ion, X plus ion, would have this photoelectron spectrum. All right, so we'll look at the electron configuration here. So this is 1s2, 2s2, 2p6, 3s2, 3p6. So there's 3 different shells here. So let's just kind of review the photoelectron spectrum. This is showing us the shell model, and then within each shell we see subshells. So the maximum occupancy of the first shell is 2, right? So it's 1s2. The s's all have maximum of 2, while p's have 6. Shell 2 and shell 3. Now, the most straightforward way to identify this ion is to use our total charge, which we know is 1. This equals the sum, or well, actually, the difference between the number of protons minus the number of electrons. So we can calculate how many protons there is. We sum up all the electrons, and we do that either through the the photoelectron spectrum or from the electron configuration. We do that. We get that the plus 1 equals the number of protons plus 18 electrons. We can solve for the number of protons, and it equals 19. We look at the periodic table, that would be potassium. So potassium would be the choice. K plus would have this electronic configuration. All right, here we have a molecule, and we usually ask questions about bond angles and geometries. So let's do that. So I'm going to identify some bonds and just work through them. All right, so bond alpha is a double bond nitrogen attached to a single bond carbon and a hydrogen. So this is trigonal planar electronic geometry because there are 3 domains. But the central atom has a lone pair, so it can't be trigonal planar molecularly. It's bent with the less than 120 degrees. Let's keep in mind, any neutral nitrogen will always have a less than sign in front of it because it has a lone pair. All right, go to beta. Here's oxygen, electronic tetrahedron, just like water. It's 2 lone pairs, less than 109. Angle theta is just a carbon-containing molecule. We don't see the hydrogens, but we know they're there from line structure ideas. And so this is tetrahedral, angle 109. The final angle, phi, is a trigonal planar. Carbon has a single bond, double bond present. Trigonal planar, electronic geometry, 120 degrees. So these are really good to practice. We got lots of problems to practice on. This way, line structures, bond angles are always good to review. So in this case, we're trying to rank the interaction of the dipole-dipole attractive forces, which is going to be proportional to the dipole. So the first thing we're going to do is just find out what are the dipole moments, right? How polar are these bonds for the molecules shown? Right, so to do that, we want to calculate delta chi for each molecule. The fluorine-iodine bond is delta chi is 1.4, chlorine-iodine 0.9, bromine-iodine 0.2. So we can see that the most polar is the fluorine-iodine. We didn't really need the chi individually because we know as we go down a column, chi decreases. So we would expect the most polar bond to form the strongest dipole-dipole attractions. And remember, and the least polar bond to have the weakest dipole-dipole attractions. And so if we wanted to show the dipole-dipole interaction for the strongest one, it would look like this. The arrowhead of the fluorine, that's on the fluorine, pointing at the most electronegative element, the most stable element, is pointing at the iodine, the partial positive charge, least stable, biggest atom. Dipole-dipole. And we would pick C. Right, so this question is, what is the interaction and what would you change to increase its contribution? Right, so first we recognize this as dispersion. It's got a big circle over the entire molecule. Partial charges are placed independent of the atom identity. This increases, dispersion increases with more atoms, more electrons, electrons and protons. So when we look at this, we can immediately cross out dipole attractive forces. And so this dispersion attractive forces, changing oxygen atoms for carbon atoms, that's not going to do it. That's reducing the total number of electrons by 2 for each atom. But increasing the total number of atoms in the chain will increase dispersion. Right, so here we're showing dipolar, right? These are dipolar moments in red, showing the arrow that way. So we would identify this as dipole-dipole attractive forces, and this is going to increase by the number of total polar bonds. So the greater the number of polar bonds present, the stronger the dipole-dipole attractive forces will be. So we would pick C. Right, the final interaction is going to be hydrogen bonding. So this is an OH interacting with an O. So this is hydrogen bonding. Attractive forces. This does not scale with the total number of atoms. That's dispersion. So that gives us answer A. Increasing the total number of polar atoms, nitrogen, oxygen, or fluorine. More sites for hydrogen bonding will increase the attractions. It is not dispersion or dipole-dipole. Right, so this molecule is often missed on our quizzes, and so I want to work it out. So the first thing you do is it's pretty good it's best to make a summary. So A is CH interacting with O, that is not a hydrogen bond. B is oxygen interacting with carbon, not a hydrogen bond. C is oxygen interacting with fluorine, not a hydrogen bond. And D is fluorine interacting with an OH bond. Absolutely a hydrogen bond. So when we look at the different options, the best choice is D. A is not a hydrogen bond because the H is bonded to a C, and that does not form a hydrogen bond. Okay, so which of the substances are polarizable here? So we worked with these three molecules in class. So there's a hint here that will not be present on the test. Polarizable means has attractive dispersion forces. Well, all molecules have electrons and protons, so all molecules have dispersion forces. So that would be, and so all molecules are polarizable, giving us answer A. All right, so this question, you're given the boiling points, and now we need to know which statements are consistent with these boiling points. Well, clearly B has the strongest attraction, right? Because it has the highest boiling point. So let's take a look at the different answers. Is it 1, is it 2, is it 3, or is it all of them? So substance 1 has a higher boiling point. This is what 1 says, because B molecules are more polar than A. That's true. There's more OH groups, more oxygen atoms, definitely more polar. That's consistent with the higher boiling point. 2 says substance B has a higher boiling point because molecules are more polarizable than A. That's true. There are more atoms present, more protons, more electrons, more polarizable. Number 3, substance 3 has a higher boiling point because B molecules can form more hydrogen bonds than A. That's true. There are more OH groups that can form more hydrogen bonds. So all 3 of these contribute to a sum of contributions. So all 3 of these are leading to a higher boiling point. All right, so this one, we're given the boiling point, and we're asked to pick statements that are consistent with these boiling points. All right, so the strongest interactions have the highest boiling point. Weakest interactions have the lowest boiling point. So substance 1 says A has a higher boiling point because A molecules are more polar than B. So that's wrong. We definitely think that would anticipate that the oxygen atom is the most polar, much more polar than carbon, and so it would form partial plus here, partial plus here, partial minus here, and so we would have a net dipole like that. So B is polar, but A is very nonpolar, just because the electronegativities of carbon and sulfur are very similar. So it's slightly polar maybe, but it's not the reason why the boiling points are different. What about 2? Substance A has a higher boiling point because A molecules are more polarizable than B molecules. For that, we need to look at the formula. C4H4S, we count the number of electrons, carbon atoms, hydrogen atoms, sulfur, total up to 44 electrons. We do the same for oxygen, 24, 4, and now 8, and we get 36 electrons. So it's clearly the sulfur, the C4H4S, is more polarizable. Number 3, substance 3 has a higher boiling point because A can form more hydrogen bonds than B. That's not true. There are no hydrogen bonds possible in either molecule. So the only possible answer here is B. Which substance would have the highest boiling point? Right, so this is an activity we did in class. So the first thing we need to do is, not exactly, but similar, we have to write the formulas. We need to know what the baseline dispersion contribution is for each molecule. And then we're going to put that here. So C4H5N, we count up the number of electrons, 28 electrons. C4H4S, 36 electrons. C2H2, 12 electrons. And C6H7N, 36. Plus 7 is a total of 50 electrons. Right, so that means we can write out a basic organized dispersion only table. And now we're going to include 15 electrons for either dipole-dipole or hydrogen bonding. So we do that first for dipole-dipole. C4H5N is polar. Thiophene is not very polar, but just for the benefit of the doubt, we'll put 15 electrons there. C2H2 is not polar, but aniline is polar, 15 electrons. Now we look for hydrogen bonding contributions. Thiophene does not have hydrogen bonding contributions. But pyrrole does. Right, so when we look at this sum, we get a total of 80 electrons, right? 80 electrons for aniline in terms of equivalent electrons. 14 electrons, just dispersion only for C2H2. Okay. Here we have 51 electrons. Thiophene. And here we have 58 electrons for pyrrole. Right, so the highest boiling point would be aniline, greatest number of equivalent electrons. Lowest would be acetylene with only 14 electrons. We could make an argument that pyrrole would be a little bit higher than thiophene, given the equivalent number of electrons. What types of intermolecular forces exist between the solvent redwood molecules? Right, so we take a look and you say all molecules have dispersion, always true. Are there dipole-dipole? Yes, because there are bent atoms. You know, any oxygen with the bent geometry, nitrogen with the bent geometry. There's actually 4 atoms that are in bent geometries with lone pairs, so they would definitely be polar. And then hydrogen bonding, yes. Is there an OH present? And the answer is yes, there is an OH. So that's going to be hydrogen bonding. This is never true, because you have to have dispersion. Dispersion must be part of the answer. All right, so let's look at some PEC diagram information. Okay, so this question is saying, like sugar into water, mixing increases when you increase the temperature. All right, so let's take a look. So what does that mean? That means if mixing increases as temperature increases, then we need to make more of it. And the more needs to be at high, remember, more is higher potential energy. So if you increase the temperature, you're going to make more of that state at higher temperatures. So when we look, and then the bottom ones, they're the same. So the only PEC diagram that's consistent with mixing increasing as you increase temperature is PEC diagram A. It also tells us that mixing generally occurs because the mixed state is at highest number of configurations. So you want to make sure that when you're looking at potential energy, a couple things. Number one, if it's higher potential energy, right, more of it is made at higher temperatures, and also the interactions are less stable, weaker. Lower potential energy, less of it made at higher temperature. Interactions more stable, stronger. Call this low and this high. Right, so that's a good summary. I want to keep in mind in terms of the y-axis. For the x-axis, high number of configurations, low number of configurations. This generally, whatever state is in this place, generally occurs. So if we do that, we look here, generally mixes. Look here, generally mixes. Generally mixes. This is generally unmixed. This is the oil and water story. All right, we did that one. Okay, so what element has the lowest, its ground state electronic configuration of 5s2, 4d6? Right, so when we look at the periodic table, what we do is we go to row 5, we see rubidium and strontium at 5s2, and then we look in the D's here, there's 10 of them, we go yttrium, zirconium, niobium, molybdenum, technetium, ruthenium. Right, so we look at 4D, so that's 4D1 yttrium, 4D2 zirconium, niobium, molybdenum. And then when we get to 6, we hit ruthenium, and that's our answer. Ruthenium 44 has krypton, core, 5s2, 4d6. Right, this is a question about vanillin. Vanillin has a melting point of 82 degrees. It has a formula of C8H8O3. Has dispersion, total of 80 electrons, 80 protons. It also has, and we look at estragole. Look at its formula, C10H12O. And so just to keep in mind, vanillin also has dipole-dipole, and it has hydrogen bonding, which adds an additional 30 electrons. So we give us a total of 110. So we go look at estragole, 60 plus 12 plus 8 is 80 electrons. Only has it has dispersion, but also has dipole-dipole. 15 electrons additional, but no hydrogen bonding for a total of 95. So based on this analysis, we'd expect that estragole cannot have a melting point similarly to vanillin, and we would pick less than 82 degrees. It's significantly lower in the total number of equivalent electrons and protons. Okay, let's talk about carbon. So generally carbon looks like this. These are the major bonding patterns that we've seen with carbon. 4 single bonds, a double bond, and 2 single bonds or 2 double bonds. Its electronic configuration looks like this. Remember, we're drawing the PS spectrum. It would look like that, 1s2, 2p2. And we need to form 4 bonds to achieve the neon core lowest energy configuration. All right, so now with that, we can kind of answer the questions. Usually we do not see lone pairs on carbon. That's absolutely true. Have 4 valence electrons. Yes, that's true. 2s2, 2p2. And can delocalize 4 electrons in their valence shell to form 4 bonds. Yes, that is correct. That's how 8 total electrons in the outer shell are obtained. All right, so with that, these are all the questions I received in doing the Pop Quiz 10. I think it's a good summary of the questions you should expect to see on Friday.